Hi, my name is Nafisa. I'll be presenting to you my research on mitigation of electrical crosstalk in silicon single photon avalanche diode, also called SPAD arrays, using binary classification, which is a main machine learning model that we will be talking about throughout this research. So my contributors and I have been working to understand how we can develop a machine learning assisted design framework to automatically predict the optimal pixel spacing or pitch size that minimizes the electrical crosstalk. But before we dive into our research goal, it is important for us to understand what the challenge is throughout this research. The primary challenge that we face is minimizing electrical crosstalk or some sort of noise that occurs between neighboring pixel size or pixels, which eventually leads to false photon events and degrades our image resolution significantly and thereby degrading our measurement accuracy. We try and understand how this pixel spacing can be optimized to suppress the interpixel interference. And we do this in order to lift our situation from manual optimization, which is very time consuming, and we want to make our solution much more scalable for industrial use because we have access to Silvaco tools or Silvaco simulation, which is one kind of TCAD tool. Even then, we see that manual optimization and um, the results that we get are not sufficiently optimized for in order to identify the crosstalk. So we introduced to you the SPAD arrays, which are widely used in applications such as 3D sensing, biophotonics, LiDAR systems, and so on and so forth. We do this because SPADs achieve high detection efficiency because of their operation. They operate in Geiger mode, which is slightly lower than the breakdown voltage occurring at 62.5 volts. And you can see this in the represented in the IV curve. We've illustrated how the SPAD array behaves abnormally at around 62.5 volts, which is when the semiconductor does not know what it is doing at a voltage beyond 62.5. The workflow is fairly simple. We try and accelerate crosstalk-aware pixel layout by optimizing using machine learning model. So we've already obtained the simulations from the Silvaco software, and these graphs show three pixel sizes. One on the left is 21, followed by 25 and 30. These pitch size is essentially the gap between each photodiode layer. So these are showing that the electric fields have been overlaid, or there is some sort of um, yeah, so there is some sort of overlapping between electric fields, which shows crosstalk. As the electric fields are separated, the crosstalk behavior is reduced significantly. So this is what we will try to optimize in this problem by using logistic regression in conjunction with binary classification. So binary classification works by taking in input data and giving you output such as 0 for no crosstalk and 1 for crosstalk. And we try to showcase this and we try to say that binary classification has successfully identified crosstalk in SPAD arrays, which has reinforced our former research results. And our model follows a fairly straightforward approach and a fairly straightforward architecture. As you can see, the data set is fed into the training data, and then it is used by pre-process. It is first pre-processed in order to reduce any and normalize any kind of parameters, and then we introduce you to the input layers, which now is again further pre-processed in order to get to the output layer, and which is where we get the predictions. We see that the binary classification model is trained to predict such crosstalk severity. And on my left, on figure 3, you can see the SPAD arrays. So this is what we have been looking at from a high level. And figure 5 shows the plots that we get from plotting electric fields against position. This has been obtained from our Silvaco software, and this is what we use as our training data set. As you can see that the position, the more we increase it, the lesser electric field we get, and thereby we can say that the crosstalk has reduced significantly. Um, the main takeaway from this research is that we get it at a significantly less time than our manual optimization. And thus, we want to say that our proposed TCAD and ML framework has been working just fine. So the more we train the data set, the robust results we get. And because such mitigation is extremely crucial for high fidelity photon detection, we think that research has immense potential to accelerate SPAD array development for industrial applications. And in future, we would also like to extend this to two-dimensional arrays and look at different parameters such as size of pixels and deploy real-time feedback. I want to thank our industry partners with Laser Components and my Equiblab members for their valuable input. Thank you so much for listening to my presentation.